So we want to consider eventually graphing a function of two variables, right? So we're going to look at this example over here to start off with, and then we will look at a couple more examples of functions of two variables and their graphs, right? Okay, but let's just review of how you actually graph a function of a single variable, and I think we talked about this already in a previous lecture, but I'll go over it again, right? Okay, so how would you graph, say, this f of x is equal to 2 minus x, right? Well, how you do it is you plot, well, two ways you can do it, right? You can either plot points, right? Okay, so what you do is you do a table here. You're free to choose whatever x values that you want, right? Although you try to choose it in some kind of sensible manner, right? And then you figure out what the corresponding y value is for each x value, right? So when x is equal to 0, you're going to get 2 minus 0, which is 2, right? And when x is equal to 1, you're going to get 2 minus 1, which is 1, right? Okay, and each of these, what it does, it determines x, y, right? So it determines a coordinate in the xy plane, right? Okay, so for example, when x is equal to 0, I'm going to have a y value of 2, right? So I have x is equal to 0, and I get a y value of 2. So let's plot that point there, right? Right, and when x is equal to 1, I get a y value of 1, right? So let's plot this point here. Okay, so notice what you're doing, right? You're free to, if you choose x is equal to 0, what you need to do is figure out what your function value is. The function value when x is equal to 0 is equal to 2, right? And what you do is you use a height somehow to indicate what the function value is, right? And the height is the y value, right? So likewise over here, when x is equal to 1, the function value is 1, which is f of 1, which is 2 minus 1, which is 1, right? Okay, and so when x is equal to 1, you indicate the function value by a height of 1 over here, right? So that is what you're doing. And let's plot our last one here. Let's plot when x is equal to 2, in which case the function value is 0. So you're going to plot this point here, right? Okay, right? So for each x value, you use a height over here and the height. So you go along over here. Well, you over here x is equal to 0 and you use a height of 2, right? Then you go along till you get the x is equal to 1, right? And then you use a height of 1 over here, which is the function value. And here x is equal to 2, you use a height of 0, right? Okay, and if this gives you an idea of what the shape of the graph is going to be. This is a straight line, right? And if it's a straight line, 2 points are good enough to determine the line, right? So all you need to do is really just connect these points over here. You don't really need even need 3, right? Just need 2, right? Okay, and to illustrate that it actually is 2 minus x, let me just put this in over here. Okay, and you see y is equal to 2 minus x is straight line passing through these 3 points here, right, on my graph. So this is the graph of the function 2 minus x, right? So your function is this over here, f of x is equal to 2 minus x, and the graph is y is equal to 2 minus x, right? Y is equal to 2 minus x. Okay. Alright, okay, so what we want to do now is we want to graph a function of two variables, right? So here I had a function of a single variable, and here I have a function of two variables, right? Okay, so it may not seem like it was a function of two variables because you don't have any y on this side, right? But it still actually is, right? Because you can put in x and y values over here, right? I'll do a somewhat more complicated example a little later on, but this one I'm using this 2 minus x because it's relatively simple to see, right? Okay, so I have this function of two variables and I want to graph it, right? Now this is a function of two variables, right? If you consider what we just did, right? What we just did is we were free to choose any x value that we want, and we get a corresponding y value, and then we plotted that, right? In this case, for a function of two variables, what you're free to choose is you're free to choose actually the x and the y, right? So you can choose anything you want for the x and the y, and then what you do is once you choose that, you substitute it into here, and you work it out, and you see what you get, right? So for example, if I choose x is equal to 0 and y is equal to 0, right? And I put that into this function. I put 0 in here and 0 in here. I'm going to get 2 minus the x is 0, which is 0. So I'm going to get 2 minus 0, which is this value 2 here, right? All right. Okay, and with that, okay, so you're free to choose the x and the y, right? So what you're actually doing is you're free to choose anything down here, right? And this here, okay, so this is a representation of a three-dimensional space, right? This is your x-axis here, this is your y-axis over here, and this is your z-axis over here, right? Okay, and what you're going to do over here, you're free to choose any xy, right? So if you're free to choose any xy, for example, that point over there in terms of xy, that is 0 0, right? Over here, this point over here, this is when x is equal to 1 and y is equal to 0, right? If, for example, I consider, say, over there, right? That point, well, it's sort of close to 1 1. Right, this point over here is x is equal to 1, y is equal to 1, right? And strictly speaking, it's in three-dimensional space, right? So as I said, this is in the xy plane, right? So the z is equal to 0, right? So this point over here is 1 1 0, right? Okay. Right, so these points over here, right, uh, in the xy plane, you're free to choose any point in the xy plane to put into your function. Okay, and when you put into the function, you get a certain value, right? Okay, so let's look at this one, right? When x is equal to 0 and y is equal to 0, I got a function value of 2, right? Now, how do you indicate that, right? In the case of when it was just a function of a single variable, right? If I had, say, x is equal to 0 over here, I worked out the height of 2, so I went up by a height of 2 over here, right? So this is x is equal to 0, and I got a height of 2, right? And you're going to do something similar over here, right? Over here, when x is equal to 0 and y is equal to 0. So remember, you're choosing x is equal to 0, y is equal to 0 down here in the xy plane. You work out a function value which is 2, right? So in other words, the height that indicates that function value is 2, right? So the point on the graph is 0 0 2, right? Which is this point over here. Okay. Right. Okay, so now let's say when consider xy is equal to 1 0, right? So remember, you're free to choose whatever you want down here in the xy plane, right? And feed it into a function. I'm choosing it in some kind of systematic way, so I choose 1 0 over here, right? Okay, and when you choose 1 0, x is equal to 1, y is equal to 0 is this point, right? And your function value over here is equal to 1, right? So from this 1 0 over here, you need to go up by a height of 1, right? I probably wouldn't get this, so it'd be somewhere over there. Okay, so I managed to get it. This point over here, this is 1 0 1, right? So starting with 1 0, and then you get a height of 1 over here, right? It how you want to look at this is going back and it's gonna hit, right? So the z level, the height over here is 1, right? Okay, and similarly I can plot okay, so when xy is equal to 2 0 and I feed this into my function, I'm gonna get 2 0 over here, right? So I'm gonna get 2 minus 2 here, so I'm gonna get a function value of 0, right? So for this 2 0 down here in my xy plane, the height is 0, right? So I don't go up at all, I just remain in my xy plane, right? So I get our next point here, which is this point there. Right. Okay, and I can keep plotting points, right? So these so far are points on my graph of my function of 3 variables, right? Right. Now let's keep plotting a couple more points when x is equal to 0 and y is equal to 2. So x is equal to 0, y is equal to 2 is this point over here, right? And then that would have, when you work that out, when you put in x is equal to 0, y is equal to 2, so the x is equal to 0, right? So you're gonna get 2 minus 0, which is 2, right? You don't get the y doesn't really influence anything, right? So you get height of 2, which is in fact the same as this height over here, right? Okay, so at 2 you're gonna get a height of 2, right? And it's probably easier for me to input. Okay, so that is your xy value, and the function value turned out to be equal to 2, so you got this point over here, and that's not correct. Right, so this should be, this should be 0. Right, so the x is equal to 0, the y is equal to 2, right? So it gives me this point over here, right? So that is directly above this one here, right? Okay, and let me do a last one. This is when right, this is when the x is equal to 2 and y is equal to 2, and when x is equal to 2 and y is equal to 2, right? What I want is 2 over here, 2 over here, so that's the point over there, and I need to work out what the function value is, right? Now the function value when I put it in is 2, 2, and the height is 0, right? So it's going to be 2, 2 for the x and y, and then the height is 0 here, right? So I'll have the point. Right, so that's that point over here, right? Okay, so I plotted, say, 5 points on my graph of a function of 3 variables, right? So the graph of the function of two variables, right? What you're doing is, in order to use the height, remember you're free to choose what the x and the y is, right? So if you want to record the height, now you need to use the z-axis. You need to use your height over here, right? So your graphs in a function of 3 variables is going to take the form z is equal to f of xy, right? Okay, in the case of function of a single variable, it was y is equal to f of x, right? But now for a function of 3 variables, you need to use a z, right? Okay, so z is equal to f of xy, right? And in this case, the f of xy is equal to 2 minus x, right? So what that means is z is equal to 2 minus x, right? And you should remember that z is equal to 2 minus x. You could rearrange Right. Okay, so if I have this z is equal to 2 minus x, I can just carry this x across. I don't really need to do this, but this is just a proof of point, right? Okay, so the x would go across here, and I get x plus z is equal to 2, right? And what you should realize is that x plus z is equal to 2 is of this form over here. And you should remember that from your 1180 here, this is equation of a plane, right? So this is an equation of a plane, right? In this case, for this plane over here, the a is equal to 1, the b is equal to 0, the c is equal to 1, and the d is equal to 2, right? So we expect z is equal, this graph over here, z is equal to 2 minus x, to really just be a plane, right? So it's just a plane, and these points are on that graph, so it's going to be a plane that's passing through these 5 points, right? And if you're graphing a plane, really 3 points would do, but I already have these 5 points, right? So to illustrate that, I'm gonna now actually just draw this graph here. Z is equal to 2 minus x, and it should pass through all the points, right? Okay, so before I input this, let's let me do something here, right? So right, so I have these 5 points, right? It is does lie on the plane z is equal to 2 minus x, but let me connect this with a polygon. Okay, all right. So this is what your graph is going to look like, right? This is, well, part of the graph, z is equal to 2 minus x, right? But it is correct, right? Now, when you try to draw the entire graph, it just gets kind of confusing, right? But this over here, this light blue face over here, that is part of your graph. Z is equal to 2 minus x, right? And let me actually now input the z is equal to 2 minus x. Okay, I'm gonna change the color. Right. Okay, so right, hopefully this isn't too confusing, right? So what's going on over here is, right, so this is z is equal to 2 minus x, right? Right, and but all these points here lie on your plane z is equal to 2 minus x, right? This sort of more of a reddish plane over here is z is equal to 2 minus x, right? So the equation of this is z is equal to 2 minus x, right? What's going on here is the software actually it always draws the xy plane, right? So it always draws this plane z is equal to 0, right? So what you're seeing over here is z is equal to 2 minus x over here, right? This is our graph, right? And it's intersecting, it also, the diagram also includes the xy plane z is equal to 0, and the two planes here actually intersect, right? And they're intersecting in this line right here, right? And you all should know this, right? That if you have two planes in three-dimensional space, provided they're not parallel, they will intersect in a straight line, right? So that's what's going on over here. So your graph over here is z is equal to 2 minus x, and the points that we plotted over here, right, lie on that graph, z is equal to 2 minus x, right? Okay, now typically when I draw and so on, right, it's easier if you're just looking at a piece of your graph over here. And the piece of your graph is this piece of the graph is sort of easier to see what's going on than rather trying to look at the whole entire large thing here, right? Okay, so let's take a look at, say, a couple more examples of graphs of functions of two variables. Right. Okay, so first one, well, the second one I don't want to look at now is this f of xy, which is 1 minus x squared minus y squared, right? Okay, so this here, to give you an idea of what it is, right, what a graph of this is going to look like, right? Let's just remember something, the function of a single variable, which is f of x is equal to 1 minus x squared, right? So if you look at this over here, this f of x is equal to 1 minus x squared, and you compare it to this, you want to realize that it has a similar structure, right? This is in a single variable, right? Okay, so f of x is equal to 1 minus x squared, right? You want to remember what that is, right? So the graph of f of x, 1 minus x squared, is a parabola, right? It's a parabola facing down because you have a negative sign, and then the intercept here is 1, right? The y-intercept is 1. Okay, so that's your graph of 1 minus x squared, right? Now, this over here, this is your paraboloid, right? Right, and your paraboloid, this is what it looks like, right? So you want to probably compare both of these, right? Okay, I mean, they're obviously not the same, right? But they have a similar sort of idea, right? So this one over here, the f of x is equal to 1 minus x squared. It has this vertex over here at the point 0, 1, right? This over here, so if you input a point here, right? So your vertex over here is the point 0, 1, right? Over here, if you look at this vertex over here, which is this point, that vertex is, so it's right there, right? That's the A over there, right? You see the point there, right? Didn't really, yeah, okay, so you've seen it a little better. Right, okay, so they have similar sort of vertices over here, right? They have a similar sort of downward shape, but this now is, it's living in three-dimensional space, while this one lives, a function of a single variable lives in two-dimensional space, right? Okay, one thing I want you to realize is that this is a function of two variables, right? 1 minus x squared minus y squared. And any function of two variables, well, almost all and the ones that we will look at, right? It's going to form a surface for you in three-dimensional space, right? So by surface, I mean, say, like a piece of paper or something, but potentially curved, right? As if you take a piece of paper and you curve it, right? Okay, so the one that we just looked at over here, this was the graph of z is equal to 2 minus x, right? And this over here, this is a surface over here, right? In this case, the surface is flat, right? Why it's a flat surface is because, well, this over here is, all the terms are linear, right? And it's, well, it's a plane, right? So that's why it's flat, right? However, this one here, right? This is curved, right? Because, well, the function itself has squared terms in it and so on, right? Okay, so this is a paraboloid, and I'd expect you to know what the graph of a paraboloid is, because we will use it when we work out certain problems and so on, right? Right. One last thing is how basically you get your you could conceptualize getting the graph of the paraboloid is if you take this over here and you spin it around this axis. When you spin it around this axis, it will trace out a shape, right? It'll trace out a three-dimensional shape, and the three-dimensional shape that it traces out is in fact this over here, right? The scaling is probably a little off here and here, so if this spins around, it'll trace out something similar to this that is a little more compressed, but it is supposed to be the same thing. The difference between here and here is the scales, right? Okay, so this is a next function of the graph of a function of two variables, and this is known as a paraboloid, right? So the graph of this function of two variables, 1 minus x squared minus y squared, is a paraboloid, right? Okay, and let's look at the next one, right? Okay, so this was, I used 1 minus x squared over here, right? So let's just recall what this graph of a function of a single variable looks like, right? Square root of 1 minus x squared. Right. Okay, so square root 1 minus x squared, should look familiar to you. What this is this is actually a semicircle, right? So it's just the top half of a circle of radius 1, right? Okay, right, now what we want to do is we want to look at this function over here, which is f of xy is square root of 1 minus x squared minus y squared, right? Okay, and once we have this now, square root of 1 minus x squared minus y squared, and you could compare it to this here, right? Okay, so this guy over here, remember, is right. This over here, this is a graph of a semicircle, right? F of x is equal to square root 1 minus x squared. That's what this one is, right? You're seeing it over here. Right? F of x is equal to square root 1 minus x squared. It's a semicircle of radius 1. But the graph of square root of 1 minus x squared minus y squared, this function of two variables, is now this over here, right? So this is a hemisphere, right? So again, it's half of something. So this is half of a circle, and this is half of a sphere of radius 1, right? Okay, and you could same sort of idea. If you take this and you spin it around your y-axis, it'll sweep out a shape, and the shape that it sweeps out is this hemisphere over here, right? If you want a better look at it, right? So this is what it looks like, right? A sphere, half of a sphere of radius 1, right? The distance from the center over there to a point on the sphere, on the hemisphere, is 1, right? Right. Okay, and just a little bit of justification that the fact that this is a hemisphere, right? So this is, if I want the graph of this over here, remember what I'm doing is I'm setting it equal to z, right? Because the z gives you the heights over here. That's how you graph. Okay, and then you have this here, and what you do is you square both sides, right? And if you square both sides, the square root sign will go away and you'll have a z squared over here. And then you can bring the x squared and y squared across, right? And now you should recognize that this is the equation of a sphere, right? Right. Okay, now if you try this, okay, so it seems as if it should be a sphere, right? This should give me, this z is equal to square root 1 minus x squared minus y squared. Should give me a sphere, right? But in fact, no, it gives me a hemisphere, right? Now, when I go along these steps over here, I get this. What that means is that this expression over here, this graph here, lies on a sphere, right? It doesn't imply that it's the entire sphere, right? One way you can see that is if you try to go backwards, if you go from here to here, right, you're okay, right? But if you go over here and you take the square root, you'd actually have plus or minus, right? And the plus is the top hemisphere and the minus would be the bottom hemisphere, right? So going backwards like this, you will give you actually both the top and bottom hemispheres. And the point is, when you go this way, you actually lose a little information, right? Okay, so these are standard functions of two variables that you should know the graph for, right? And as I said, we'll have questions based on these, so you should get familiar with them, right? Your radius doesn't always have to be 1 over here, right? Here you see in that your radius is 1, right? If I change this, for example, to say 4, right? What I'll get is something of radius 2, right? Would need to scale down a bit, right? Okay, and you see now this 2 over here is to indicate that this is 4 is 2 squared, so the radius is now 2, right? Okay. All right. Okay, so the last thing in this review for partial derivatives is an interpretation of numerical values that you get from partial derivatives, right? In other words, a partial derivative, you evaluate it at a specific point, right? Okay, and how we can interpret that is as slopes of tangents, right? So let me just remind you what was happening in the normal one variable case, which is something that you know from your from high school, right? Okay, so if I have a function of a single variable, for example, x squared, and we did this example in the last lecture, previous lecture, right? So if f of x is equal to x squared, right, I can get the derivative, which is 2x, right? And if I evaluate that derivative at x is equal to 1, I get an actual value, right? So evaluating this, x is equal to 1 will give me 2 times 1, which is 2, right? Okay, so this 2 has an interpretation as, or is equal to, slope of a tangent, right? And the tangent, where we taking the slope, for which we're taking the slope, right, is this tangent over here, right? So everything is going on at x is equal to 1, right? We're looking at this function, x squared. We're looking at the derivative. We're looking at the derivative when x is equal to 1, right? So the tangent that we're looking at will have to be, I mean, it makes sense that it's associated to x is equal to 1. So over here, this is when x is equal to 1, right? Okay, so this is where x is equal to 1, and then the y is equal to 1 over here, right? And the tangent that we're looking at is this tangent here. And the slope of this tangent is 2, right? That is interpretation, right? Okay, so f prime derivative evaluated at 1 gives you a value, and that value is equal to the slope of a tangent at the point, which is x is equal to 1, right? Okay, so what we want to do is we want to consider the same, we're going to consider something similar, right? Okay, so your partial derivatives, if we evaluate them at a specific point, they're going to have a similar interpretation. So that is what we want to discuss now. Okay, all right, so As I just said, right, if I have a function of a single variable and I look at a specific value, the example that we just looked at was the a was equal to 1. Then when I work that out, right, and what I just worked out previously is that the f prime 1 turned out to be equal to 2. I will get some value, and that value is equal to the slope of a tangent, right, at a point x is equal to a, right? So for function of two variables, right, your partial derivatives are also equal to slopes of tangents, right? And it's slopes of tangent corresponding to a specific point, right? Okay. Right, so let's look at this example here, right? This example, the function that I'm looking at is f of xy, function of two variables, which is 1 minus x, right? So this is similar to the example that I did probably like about 15 minutes ago, right? Which was 2 minus x, right? But now this is 1 minus x. Okay, so this is also going to be, the graph of this is also going to be a plane, right? The plane z is equal to 1 is 1 minus x. And it, right, and you can figure out the location of the plane by plotting a couple of points or graphing it on a computer algebra system, right? Okay, right, so this is the graph of my function of 1 minus x, right? Okay, so the graph of the function of this function forms a surface in three-dimensional space, right, which is a plane. Right. Okay, so now what I want is, okay, so this is my function of two variables, f of x, y is equal to 1 minus x. And I'm going to take derivatives, right? Okay, so when I take derivatives in my function xy is equal to 1 minus x, function f of xy is equal to 1 minus x, your derivative with respect to x is equal to minus 1. If I differentiate this with respect to x, this minus x, when I differentiate it, will give me minus 1. Okay, and when I differentiate with respect to y, I'm just going to get 0, right? Okay. Right, now what I'm actually interested in is at a specific point when xy is equal to half 0, right? Okay, so it's not drawn on this diagram in the notes, right? But if you look at this, this is this point over here, right? This point over here is a half, 0, a half, right? Okay, so the x is equal to half, the y is equal to 0. So the point x is equal to a half 0, right, is actually right down there below this one, right? So the half 0 is over there, right? Anyway, right, so what we do is we evaluate a partial derivative of f, the partial derivative df dx at this specific point, which is a half 0, right, which is somewhere down there, right? Okay, and when we do that, what we're going to get is we're going to get, if I put a half 0 into this, right, I will get minus 1. It doesn't make a difference what I put into it. It's just that this function is so simple, right? And the fact that when you differentiate it, you just get constants over here means that um, uh, if I can put in anything and I will get minus 1. So similarly here, I get a half. If I put in a half 0, I'll get minus 1, right? And the reason why it's basically it's you're just getting constant derivatives is because it's a plane, right? When you have a plane, it means that your derivatives, your partial derivatives are constant. But anyway, let's so at a half 0, the partial derivative is minus 1, right? So the partial derivative with respect to x at a half 0 is minus 1. Okay, and your partial derivative of y at a half 0, right? Again, it doesn't make a difference what you put into it. You'd always get 0, so you get a 0 over here, right? So one more time, this only works if this is a if this function over here is linear, right? Or say very simple, right? If you have a more complicated function, this isn't going to be the case, right? You would need to actually work it out. In this particular case, it's relatively simple, right? Okay. Right. Okay, so now at this half 0, right? If I substitute half 0, right? which is xy, right? If I put that into this equation and a half 0 over here, I'm going to get a half. When I put a half and 0 into this, I'm going to get 1 minus a half, which is a half, right? So the z value when I put in a half 0 is equal to a half, right? And you've seen it over here, right? Okay, so the x is equal to half, the y is equal to 0, and the z is equal to half, right? And the point is that the point is that this point over here, right, this half 0 half, right, is on the graph of this function, right, is on the graph of the function of two variables, in the same way that how this point over here was on the graph of your function of a single variable, right? Okay, so when you're looking at tangents, for us we're looking at tangents to a point on the graph, right? So here in this case, the point on the graph was 1, 1 in your single variable case. And remember this gray plane over here, this is your gray plane over here. This is your graph, right? Okay, so and this half 0 a half is a point on the graph. So you have if you compare, this is the case of the single variable and this is the case of when you have a function of two variables, but you have similar ideas, right, between them, right? So if you're looking at uh, tangents, what you want is tangents to a point on the graph. The graph over here, in this case, is this parabola over here. And in this case, for the function of two variables, the graph is the plane, right? This is a point on this graph over here, and this half 0 half is a point on this graph here, right? Okay, and now what we do is, well, we want an interpretation of this partial derivative here, right? Okay, so we want an interpretation of this partial derivative, right? When we worked it out, we got -1, right? So how can we interpret this -1, right? And how can we interpret this 0, right? So comparing to this picture over here, right? These values -1 and 0 have to be slopes of tangents, right? So this, when we worked it out over here, and we got a 2, right? The 2 was the slope of this tangent here, right? In this case over here, this -1 and 0 are going to be slopes of tangents, right? And well, what tangents are we talking about, right? So this is the point in the graph, and the two tangents that we're talking about is this one over here. This is line A. So if you look in the notes, I probably zoom back in, you can read it. This is line A over here, and then this is line B over here, right? Okay, and the point about line A is overall, okay, so for line A, what's happening is the y values are not changing, right? The y values are fixed, right? Okay, and for line B, right, the x values are not changing, right? The y values can change, but the x values remain constant, right? Okay, so we look at this point over here, right? So this line A, what it's doing for you, it's a tangent in the direction x if you want, right? If you project this line A, you'll realize that it will lie along the x-axis over here, right? And what you want to do is you want to consider what's happening. Now, this is your positive x direction over here, right? You're moving out this way, right? So if you over here and you consider what's going on, right? When you're moving in this direction, x direction over here, what's happening to your function values, right? Well, these function values are higher and it's dropping down, right? So your function values are getting smaller and smaller. Well, they're getting smaller, right? Okay, so the fact that your function values are decreasing, right, is telling you your function is decreasing in the x direction where you hold in the y constant, right? And rate of change, right, in the x direction when you hold the y constant is actually just partial derivative, right? Okay, so the rate of change in this direction over here, you can see it's negative, and that's where this -1 comes from, right? On the other hand, if you consider along line B now, right, if you notice, right, I don't know how well you can see it from this diagram, but if you, so this, in this direction over here, what's happening is that the y values are changing and the x values are fixed, right? So what you want is, you want to determine how your function, the function values are changing as you move in this y direction, right? Okay, so what you want is rate of change in this y direction while you keep x fixed. And what you want to notice is that you're not actually moving up or you're not moving down, right? You're actually just staying at a constant value, right? Okay, so when you move in your y direction over here, right, along this line B, you see in graphically that the rate of change in fact is 0, right? There is no change, right? And if there's no change, the rate of change is 0, and that is actually where this, that is how you interpret this 0, right? Okay, so your partial derivatives could be interpreted as slopes of tangents, right? So we're interested in this specific point, half 0, so half 0 is down there. You find the point on the graph, which is a half, 0, a half, which is this point in the graph. And then what you do is you look at tangents, right, in the x direction, and tangents in the a tangent in the y direction, right? The slope of the tangent in the x direction passing through the point of interest, right? This is negative, and that agrees with this -1. And the slope of the tangent in the y direction is 0, right? And that agrees with this 0 over here, right? So that's your interpretation of partial derivatives, right? Partial derivatives, when you evaluate them at a specific point and you get an actual value over here and you get a value over here, those values are equal to the slopes of certain tangents to the point. Okay.